So as per our previous discussion, we have seen that if we consider this particular data set in which we have petal length, sepal length as the features, and this is the label. Then if we start with suppose petal length, then we'll select a value from among these or a particular value such as let us select 2, which lies over here. Now we'll divide this particular column of petal length into two parts. One is all the values less than 2 and all the values greater than 2. So if the value is greater than 2, as per this condition, it will be no. And if the value is greater than 2, yes, then it is this. Okay. So if we see the plane, then here they have divided that if the petal length, which is plotted along the y-axis, we consider 2.0, values less than 2.0 will be this particular rectangular portion, and values which are greater than 2 will be in this particular rectangular portion. Now further, we can split as per the sepal length, which is plotted along the y-axis. When sepal length is plotted along the y-axis, we can see that if we take a particular value from among the sepal length, let us take the value, suppose 3, or let us take 1.5. Suppose we take 1.5, that value will come somewhere here. So all values less than 1.5 and all values greater than 1.5. Now, if petal length is less than 2, we know that we will go for the left hand side. And if petal length is greater than 2, we'll go for no. So sepal length, we have it. Now, if sepal length is less than 1.5, it is less than 1.5, this part, and if it is greater than 1.5, this part. Now, suppose we are confidently saying that our petal length is greater than 2. If petal length is greater than 2, we'll only focus on this particular region. And in this region, we want to find what is the class of the flower. So in this particular region, if we consider sepal length as greater than 1.5, then it is this particular rectangle. If we consider this particular rectangle, then we can say that petal length greater than 2.0 and sepal length greater than 1.5. That is this particular region. And if it is this region, then we are saying that the flower is of the type Virginica. Okay, so this is how we are dividing in case of numerical features and categorical labels. This we had seen last time also. Now let us go for the pseudocode. In pseudocode, we begin training the dataset, which should have some feature variables, and the output may be either continuous numerical, that is regression, or it may be specific categories like classification. We need to find out the best feature in the dataset to split the data. We have always seen that we'll begin with the particular feature, all the possible values of those features. Once we do the splitting, we'll consider another feature here, all possible values of these features. After doing the splitting, we'll consider another one feature. Here also we consider features. Here also. So in this way, we are splitting. So in which order to select? This is suppose feature 1. This is some other feature 2 that we have considered, another feature 3. So in which order we need to select the features? Which should be this one, which should be this one, and so on. So that determine the best possible sequence. That means first feature 1, then feature 2, then feature 3. This sequence should be the best one, best possible sequence in the data set to split the data. And we need to define the best feature. Now splitting the data into subsets that contain the correct values for this best feature. The splitting defines a node on the tree. It is each node is a splitting point based on certain feature. So at each node, we perform certain splitting. And we need to recursively generate the new tree nodes by using subset of data created from step 3. That is what we have seen, right? In our previous example, we had outlook over here, and then we had the options of rainy, sunny, and suppose windy. Then we need to generate another hierarchy over here, and then another hierarchy, and whatever the labels we have reached here, that means suppose 3 yes and 2 no, only these we consider further while splitting. That means while generating the new tree nodes, we need to use the subset of data created at the previous step. Only these yes and no's will be considered further down the hierarchy in this rain branch. Right? We have seen this. So the conclusion is that programmatically speaking, decision trees are nothing but a giant structure of nested if-else condition, right? And mathematically speaking, decision trees use hyperplanes, or you can say geometrically speaking as well. We know that decision trees are hyperplanes which run parallel to any one of the axes which cut the coordinate system into hypercuboids. Now, this is what it is talking about 3D space. In 2D, what we'll say that we are using lines in order to cut the coordinate system. Suppose this is our coordinate system, then these lines cut the coordinate system in order to form certain blocks or spaces like this. Suppose we take it into 3D. For example, if we have 3 classes, Setosa, Virginica, and Versicular, then for these 3 classes, we should have 3 axes. For example, here we have only 2 axes, that is sepal length and petal length. Suppose we have another one feature, maybe flower size or something like that. Then we'll have another z-axis. This is one axis. This is another axis, x, y, and we may have another axis, z. Then this will become a 3D coordinate system. So these lines, which are parallel to these axes, will become planes actually. A plane can be identified as a particular sheet kind of, which will be parallel to this coordinate axis, any one coordinate axis. For example, this line and this axis are parallel, this line and this axis are parallel. And then when we use these planes for cutting, they will form cuboidal spaces or sections in 3D space. That is why it is mentioned cuboidal over here, hypercuboids. Now certain terminology. That means when we construct the decision tree, the first node which contains some feature is called as root node. And these what we are going to do is called as splitting. Then this is the branch, or you can say stem. Then we have decision nodes. Decision nodes means you're taking certain decision here, whether sepal length is less than 1.5 or not. And then final, these nodes, which have no further splitting. That means no further child nodes are the leaf nodes. And this highlighted subpart of the entire tree is called a subtree. Now, CART is a popular term which stands for classification and regression trees. These trees can be used for classification purpose also, in which we have categories at the nodes, or for regression, in which we are taking decisions that whether the values are less than a particular value or greater than a value. So the logic of decision trees can be applied for regression as well as classification. Now, there are certain advantages and disadvantages as well. Now, the advantages are that it is intuitive and easy to understand, and minimal data preparation is required. It is not necessary that we have large data sets for preparation. We can use minimum data preparation, and also no need of normalization and standardization. That means sometimes the features are not suitable for getting higher accuracy on training. That time we do normalization or standardization to get the feature values, especially if categorical, into the same range and so on. However, those things are not needed over here, which we have seen earlier as well. And then the cost of using this algorithm is logarithm, because whenever we have a tree-like structure, in order to search in the tree, the time complexity to search any particular value or any particular condition in the tree is log of n, where n is total number of nodes. So whenever we have logarithmic complexity, it is always better than the linear complexity, since it is a tree-based data structure. Searching complexity is less. And then it is a more programmatic approach rather than a mathematical approach, because we know that it is nested if else by the end of the day. So there is more of programmatical approach. Decision making is involved. And speedily it works on the data set. And the disadvantage is that it is prone to errors for imbalanced data sets. Imbalanced data set means, suppose you have two particular classes, such as yes or no in your label. If you have two particular classes like yes or no, and suppose 98% are examples where all the labels are yes only, and only 2% examples have the label as no. Means the model will get trained maximum on the label having yes as the label. So if no is lesser, then model does not get trained well for the examples where the output is no. Hence, it will be overfitted over the examples where the output is yes, and it will not give good accuracy in case the output is no. And it may predict the wrong output. In case the output is no, it may predict it as yes. So this is imbalanced data set. And another thing is overfitting. That means the way in which we are building the tree is what? Sometimes we use the condition that if A is greater than 2, this particular section, if not this particular section. We are using such a condition in case of regression decision trees. So this 2 value is a constant in this condition. But what if the data set changes? This 2 will also have to change accordingly for efficiency. So if we are using such conditions over here, which are specific to the data set, then it is well trained on this data set, but on other data sets, it will not perform that well. Hence, it is a case of overfitting. So these are the advantages and disadvantages. However, there are certain unanswered questions. That means how to decide which column should be considered as the root node. That means from which feature we need to start splitting. That has to be decided. How to decide that efficiently so that in minimum splits and in minimum time we can find out the answer. That is one question that has to be answered. Second is how to select the subsequent decision nodes. After this particular feature, F1 that you have selected, F2 how to select. What should be the condition over here? So such things also have to be decided efficiently. And then lastly, how to decide the splitting criteria in case of numerical columns. We know that if we take a particular numerical feature, it has so many values. In order to restrict the use of so many decision nodes, what we did is we selected one particular feature value and we selected the condition that greater than that value will go left side, suppose, and less than that value will go on the right side, suppose. But then how to select this particular value based on which we are developing two sides of the tree? So that is another question that needs to be answered. Next, we'll see the concept of entropy. In the layman terms, what we can call entropy is, it is a measure of disorder, or we can say entropy is a state of randomness. The state of randomness or a state of scatteredness. So, more the randomness, we can say more the entropy. So, you can also call it a state of impurity or purity. That means how much pure or how much impure. For example, if we consider the 3 states of water or 3 states of liquid, we know that we can have liquid in the form of ice or normal water, that is liquid, and in the form of vapor. That means solid state, liquid state, and gaseous state. So here, the molecules of this particular ice block are in a good, well-arranged structure, and they are close to each other. They are fixed. They are not mobile, or they cannot move randomly. In water, those molecules are a little more free apart from each other. And in the gas, however, they are also linked to each other. And in gaseous state, they are very random. They don't have strong bonding between them. So here what we'll say that there is less scatteredness or less randomness, so entropy is low. Here there is more scatteredness, so entropy is moderate. And here there is maximum scatteredness, so entropy is high. So in this way, we can explain entropy. Now, in terms of data science, what we can say that if we take this particular example, here we can see that we have two classes. So this is a classification problem. Here also we have two classes, which are indicated by red and green. Red and green. Now, if the two classes are in almost equal numbers, as you can see, we can have a kind of separation over this much is red and this much is green. It means somewhat equal quantity. Or another case can be maximum of one particular class and minimum of the other class, as in second case. So here we can say that we are not confident. Why we are not confident? Because here we are not confident because here we cannot exactly say that there is more chance of red or more chance of green. We are not confident. That means we will not have accuracy over here. There's no accuracy over here. However, here we can confidently say that maximum prediction will be red, isn't it? As per the dataset, we are confident enough that maximum times the probability of the class being red is higher. And here we have accuracy in saying that, yes, the class red is of higher importance. So these are the two things that we infer from here. Also, we can say that here we are not confident because we have less knowledge. And here we are confident enough because we have more knowledge or more confidence. Next, we can also say that here category 1, suppose this is category 1, this is category 2. The chances of category 1 are definitely greater than, may be equal, not greater than, it may be equal to category 2, almost, approximately. And here the chances of category 1 are definitely greater than category 2. So if we have less knowledge, we are not confident, we don't have accuracy. This is because there is more scatteredness. So here there is more scatteredness. And if more scattered, we can say more entropy. And here, since it is less scattered, we can say here there is less entropy. So these are some conclusions that we can define. If the number of categories is supposed to, and they are almost present in equal proportion, equal probability, equal chances of them being predicted, then we have less knowledge and not that confident, we don't have accuracy. If there is no accuracy, it is because there is more scatteredness. This is an important conclusion. And if there's more scatteredness, there's more entropy. Whereas if we have more confidence, we have more accuracy, then it indicates that there is less scatteredness in the data points plotted, and hence there is less entropy. So we can have a proportionality over here. That means if we have knowledge, it is inversely proportional to entropy. More knowledge means more confidence, means less scatteredness, means less entropy. Okay. So mathematically, how to calculate entropy? Every time we cannot perform data visualization, or maybe if there are more number of classes and they are almost in proportion, some are not in proportion. In case of such complex examples, we cannot do it by observation. Hence, we need to calculate entropy mathematically. So the mathematical formula for calculating entropy is summation of minus pi log of pi to the base 2 or to the base e as well. Now, what does this formula mean? That entropy of a particular feature or a particular data set can be given by minus p category 1. This I stands for the particular category. Suppose we have 5 categories, then I will go from 1 to 5. So category 1, log of P of category 1 plus, again it is summation, so again minus probability of category 2 log of category 2. Again it is summation, so plus or minus and so on up to category n. Okay, so this is the meaning of that, where Pi is simply the probability of that element or class or category in the data. For example, if our data has only 2 classes, then which will be the 2 categories of output or label? Yes and no. So instead of category 1, we can write yes, and instead of category 2, we write no. So that time the formula will become this one, minus P of yes and minus P of no. For example, in this particular data set, we have 2 features, salary and age, and based on that the expenditure, or whether he will purchase the item or not. So we have only 2 classes, yes and no. So if we want to find out the probability of yes, we know that probability is given by the formula of the requirement upon the total availability. So in such a case, what we'll write it as, our requirement is for the class yes. So yes appears 2 times and total examples are 1, 2, 3, 4, 5. So 2 upon 5. So that is 2 upon 5. Similarly, probability of no, you can calculate by saying no appears 3 times. So 3 upon 5. Or what you can do that, probability of no is nothing but 1 minus probability of yes. That is 1 minus 2 by 5. That means 5 minus 2 by 5. That is 3 by 5. Why we can say probability of no is 1 minus probability of 2? Because a probability of n is 1 minus probability of yes, because the total probability is 1 and the total types or categories are only 2, that is yes or no. I hope you know how to calculate probability. Then you can find out the log values, then perform mathematics and find out the entropy for this particular data set. So data set entropy is found out based on the occurrence of the labels in the data set. Similarly, we have example 2. Here the probability of yes is 1 out of 5 times. And probability of no will be 4 out of 5 times. If you want to check whether you're calculating probability correctly, then total probability should be 1. Means probability of yes plus probability of no should be equal to 1, which is satisfied over here because 1 by 5 plus 4 by 5 is 5 by 5 is 1. Another case is what? When you have all the classes which are same. For example, here the label is only no. There is absence of yes. That means the probability of no will be, the required is how many times? 5, and the total times is also 5. So 5 by 5, probability is 1. Total probability is equal to probability of only one category is equal to 1. If probability of no is 1, probability of yes as per observation or as per calculation also is 0 out of 5 times, which is 0. Hence, we can have probability of yes as 0 upon 5 and probability of no as minus probability of no as 5 by 5. And whenever you have any one particular feature as total, that means if in the labels there is only one type of a value, or you can say that all the labels are same, that time always entropy is 0. Why is that so? If we plot the graph, we will have only the same colored circles. Previously what we had 2 classes. That is why due to 2 classes, we had 2 kinds of colors in the plotting. But now we have only 1 class, so only 1 kind of color will be there in the plotting. That means we are very confident that it is that class only. That means we have more knowledge. That means we have less entropy. Similarly, we can have three classes also in our calculation, such as yes, no, and maybe. So again, we'll have an additional term. Till now, we have calculated 2 times, now 3 times. So probability of yes will be 2 out of 1, 2, 3, 4, 5, 6, 7, 8. 2 out of 8 examples. Probability of no will be 3 out of 8 examples, and probability of maybe is 3 out of 8 examples. So if we add all these probabilities, the summation will be equal to 8 upon 8, that is 1. Okay, so here if we consider a kind of splitting, if we have the categories as if we have 2 kinds of categories, that is yes or no, and if we are splitting by a particular feature, as we have seen, we take a particular feature, what are the values of that feature, or if it is categorical, what are the 2 categories which are possible for that particular feature, and then total number of yes and no is here. If this is the category of the feature, these are the number of yes and no. If this is the category of the feature, these are the number of yes and no. So if we have all categories which are yes type only, what will be the entropy? That time the entropy will be 0, as discussed previously. If all the labels are of same type in the output label, then it is said to have 0 entropy. There's another case wherein equal number of yes and no. This case we have seen on the left side, we had plotted it. If there are equal number of yes and no, entropy will always be 1. Okay, if there are equal number of yes and no, entropy will always be 1. Okay, so we have calculated entropy for this particular node. How? Considering the number of yes and no present at this particular split, and entropy of this particular node by considering split at this particular node. Now, if we plot a graph of probability versus entropy, then what we'll do, probability versus entropy, how the graph will come is, suppose we consider either, if there are 2 classes only, then if we consider the probability of class 1, probability of class 1 will always range from 0 to 1. Okay, so if the probability of class 1 is 0, that means there's only class 2 over there. If there is only class 2, that means what? If there is only class 2, that means we are very confident that there is only class 2. If we are very confident, then we can say that entropy is 0. So if probability on the x-axis is 0, then entropy on the y-axis will also be 0. Similarly, if probability of class 1 is over here, it is 1. That means what? Class 2 is absent. That means we can say label is definitely class 1. That means we are very confident. Then again, entropy, if x is 1, entropy on y will be 0. Whereas if probability of class 1 of class yes is half, then probability of class 2 will also be half. If probability of class 1 is half, definitely probability of class 2 is also half. If there are only 2 types of classes, in such a case, what we can say that the entropy will be 1. We have just now seen over here, if probability of yes and no is equal, that is 1 by 2, that time probability will be, the entropy will be 1. Okay, so in this way we have considered cases and we will get this curve on the graph. So remember, this y-axis is entropy. How much is the entropy? Which will range from 0 to 1 in case of 2 classes, and probability also goes from 0 to 1, which is on the x-axis. So the observation is that more the uncertainty or randomness or less confidence, if we are more underconfident, more is the entropy. And for 2 class problem, minimum entropy is 0, maximum is 1. There are 3 classes, 4 classes, and so on. Maybe entropy will be greater than 1. But if there are 2 classes, minimum entropy is 0, maximum is 1. And if there is only 1 type of class, entropy is 0. If there are 2 types of classes in which we have half of probability for both, then entropy will be 1. And we can consider log calculation with base 2 or base 0. So entropy versus probability. In case of entropy versus probability, if we have entropy on this axis, if we have probability on this axis and entropy on this axis, which is denoted by h of s or h of dataset, then we can have, suppose we have probability of positive class or probability of the class yes over here as 0. Probability of the class yes is 0. That means all the labels are of the class no. Then if probability of class yes is 0.2, that means little bit of positive class and maximum of negative class. Then if probability comes at 0.5, we know that negative class and positive class are equal in proportion. If probability of class increases more, negative class probability decreases. If probability of class yes increases further, probability of class no is decreasing. And if probability of class yes is 1, that means total probability is of the class yes only. Positive class, that means probability of class n or no or negative is 0. So in this way, we are plotting the graph also for our convenience, as at the same time plotting the curve of probability of one particular class versus entropy of the data set. So this is what we have seen in our previous, in this particular lecture. And further, we'll continue this topic for entropy for continuous variables, in which we have numerical values in the next lecture. Thank you.